Hello and welcome to C++ Weekly. I'm your host, Jason Turner. Once a week, I pick some topic of interest in C++ and dig into it with some live coding. In this episode, I'm going to discuss building C++ 14 programs for the Commodore 64. And the very first question that you should probably ask is why in the world would we want to do such a thing? And the reason is because modern C++ can be compiled to extraordinarily efficient object code. And this is something that I'll demonstrate using the excellent compiler explorer from Matt Godbolt. So the website starts you out with a simple code editor on the left and an assembly output on the right. We are using GCC 6.1 in this example, and we have all optimizations and warnings turned on and the compiler set to C++ 14 mode. So in the Commodore 64, it is possible to change the border color of the screen by writing to the memory location D020. And we can do this in our main. So what we have here is we have the memory location D020, which we are using a reinterpret cast to convert that to a uint 8, that's an unsigned 8-bit integer, pointer, and we are dereferencing that pointer, and we are assigning it the value 1. And as you can see over here, this very simply moves the value 1 into the memory location 53280, which is the same as D0280 in hex. And then it uses XOR to zero out the A register and returns from main. This is because main is expected to return 0 in the case of a success, which is the standard here to by default return 0. And as you can see, if we update this to return 1, we are instead moving 1 into the A register. So this would get a bit messy pretty quickly, so let's go ahead and create for ourselves a little handy function to get access to a particular memory location. Now all of the memory locations on the Commodore 64 are in 16-bit. It has 16-bit addressing with 8-bit data. And now you can see we are getting the exact same results here in our main. We have this new function called memory, but it's not actually being used. The program is going to jump into main, it'll execute this code, and everything will continue as it did in the previous example, and memory is just unused, it's just sitting out here. Now, we need to mark this volatile, because otherwise the compiler is going to start to outsmart us, and it's going to think, well, I've already written to that memory location before, so I can save a couple of steps. But in this particular case, we want to know that we're getting the same memory location back each time, and that we're directly accessing the hardware of the Commodore 64. So that's cool, but where can we go with this from C++ 14 standpoint? Let's say we want to create a function that updates the border, and we want to take a color value that we want to set it to. And we can do this with a lambda and using auto. So now in here we can say ox d020 equals color. And we're getting a warning from the compiler that we have created this lambda but not used it. So now we're going to set the border color to 1 by using our lambda function. And we are continuing to get the same output. This is pretty handy. So let's take it another step, and we really want to give these colors names. So we're going to create a strongly typed enum that is of type uint8t. And we're going to give it a couple of values to start off with. And you could continue down for the 16 colors that the Commodore 64 supports. And now in here we can say, well, what we really want to do is take an object of type color, and then we need to static cast the value of it back to a U88T because implicit conversions with strongly typed enums are not allowed. And now when we call our update border, we can call it with the color white. And as you can see, we are still continuing to get the exact same results. And this keeps working well for us. In fact, say we want to get the current joystick value. The first 5 bits of each joystick port memory location are up, down, left, right, and fire button. So let's create for ourselves a little struct called Joystick State. And let's have its constructor take a memory location by copy here. And now what we have for the joystick state on each port of the Commodore 64 is that if the bit is set to 0, then that state is true. So we have up is bit 0, down is bit 1, left is bit 2, right is bit 3, and fire is bit 4. And I don't know about you, but I don't really like doing a whole lot of binary operations in my head, so I'm going to do something like this. Let's assign the value up to not bit test of bits of 1. Down is not bit test bits, 0, 1. I just did another zoom in level here. Hopefully things have been visible up to this point. Now we need to actually create those. And fire. Now, of course, we don't actually have a function called bitTest yet, but we can create that easy enough. So we want to return true if that bit results a bitwise AND of the particular bit number shifted in does not equal 0. And now we can see our bit test function exists here and our memory function exists, but there's no one actually using the struct Joystick State, so it's not really doing anything yet. So let's now create another function. I'm going to say that's a handy little function that will return the state of the joystick port A, and we will do that by grabbing memory location DC00. And now we can see our joy port A, and wow, that looks like an awful lot of code going on here. Oof, hopefully it's okay. Now let's do this. We're going to create a little while loop. While true, if joy port A dot fire, then I want to be setting the border color to white, else I want to update the border color to black. And now what we need to look at is our main again. And we see that main is not actually calling any of these functions that we have created. And in fact, it has compiled down to only 8 CPU instructions, we have all of this high-level code effectively utilizing C++, 11, C++ 14 techniques. We could be throwing in const expr here. We could be doing anything that the compiler can do at compile time and optimize away for us. This data structure that we created for the joy state has completely gone away from our code. So we have 57 lines of modern C++ that is compiled down to, as I said, 8 CPU instructions. Oh, and we can see that we actually have a bug in our code right here. We're not meaning to set this value to 1 every time. We simply want to return the volatile value. So now we can see that the results of this are actually quite readable. We are copying the memory location for the joystick port A into our A register. We are testing A against the value 16. If it does not have that bit set, the fire bit, then we jump to memory location L7 here, the label L7, where we set the border color to 0. Otherwise, we continue. We set the border color to 1, and then we reread the joystick port and jump back into our loop here. So it does an initial setup case. It looks like it's done a partial loop unrolling for us. But now that we have this, we're kind of left with the question of what do we do with this? How does this help us write Commodore 64 code? Because if we haven't been paying attention, this is all x86 assembly. So we're going to take this source program, copy it. We are going to now play with a little tool that I wrote called x86 to 6502, which is a reassembler. And here is our program that we just copied and pasted from gcc.godbolt.org. And we're going to compile it here with G++5, 03, C++14, test joystick, and we're going to ask for assembly output, and we're going to be asking for that output to be dumped to the console. So we can see here the program. What we are largely concerning ourselves with is main, and there's a bunch of extra cruft in here, but the main part of our program that we were looking at is right here. And now we can take this and we can pipe it through our x86 to 6502 translator. And what we have is a few errors in that it was unable to parse all of the functions at the top, but those don't really matter because it stripped away all of the unused functions, and we have our 6502 assembly equivalent. So we are loading the value of 56320 into register A. We are doing our bitwise and our comparison. We are branching on 0 to L7. L7 is jumping back up to L6, L10. Everything, every piece of this is here. So we were using the port A fire button on our joystick. So we will now take this code and we're going to pipe it through sed because we need to strip off the leading tabs from all of these lines for the sake of our Commodore 64 assembler, but I've left them in for the sake of readability when I'm working on the code myself. So now we have these values. We're going to copy them. And now we have our Commodore 64 emulator with Turbo Assembler running. And we are going to paste in those assembly instructions that we just compiled from C++ 14 and then did a reassembly of them from x86 assembly to 6502 assembly. And we are going to assemble this. And then we're going to start the program. And now, after a quick adjustment to my emulator settings to take into account that port A actually maps to port 2 on the Commodore 64, we can see that pressing the fire button on joystick number 2 changes the background color to white. which is exactly what we expected it to do. And now back in our C++ code, we can see I promised that we would be using some C++ 14, and I maybe not quite got there, but really, we could just do auto return type deduction on this and auto return type deduction on this, which is kind of silly, but it really doesn't change the program at all. And it's just to prove that anything that we can do that keeps the code simple, we don't want to do any dynamic allocation, we don't want to really work with anything greater than an 8-bit value, because that has not been taken into account yet. And we probably don't want to call any standard library functions, although there are many, especially the C++ standard algorithms, that just get compiled away also, like many of these other examples. And, there's all kinds of things that we could do here that really wouldn't change anything at all, but what we have is our black and white, and we could continue to add more colors to this example or anything else and just keep it simple, and it works. This is not hand waving. This is a real project, and you can check it out on my GitHub page. As you can see here, it's at lefticus/x86-26502. The source is all up, and some example usage. So give it a try. Let me know if you come up with anything interesting.
Be sure to subscribe, follow me on Twitter, and check out any of the links below.